All right, so let's start thinking about looking at a molecule and being able to tell whether it's going to be acidic, basic, or kind of neutral. And so remember, acids donate H plus, and so this part of kind of is very obvious, but can kind of be overlooked. So in order for something to be an acid, it almost always has to have an H plus or a hydrogen somewhere on the molecule. We'll learn one exception to this, but for the most part, you have to have an H to be able to act as an acid. And it's not just that you have to have an H, we have to take a look at different types of bonds. So for example, why is HF, an HF bond, acidic, but a CH bond isn't? Right, and so what we kind of want to think about here is this bond strength. One of them is strong, one of them is weak. And so let's draw an H, and then an F, and then a kind of an H, and then a C. And remember, what's determining where the electron is spending its time is the electronegativity. So fluorine itself is a very electronegative element, and so we have a dipole here. And so the electrons are spending most of their time on fluorine and just a little bit of its time on this hydrogen. Maybe something like that, I don't know. And so this bond is very polarized, and so it makes this bond right here very weak. Whereas the electronegativity between carbon and hydrogen, although there is a dipole here, it's not nearly as strong, and so the electrons are shared at least more evenly. And so that makes this bond stronger. And right, in order to release an H plus, we have to break this bond, and so the weaker bond is going to break easier. And so the bond must be polar, with the hydrogen being partially positive to be acidic. So for example, HLI, HC, and then HF, right? If we draw the dipole arrow over here, hydrogen is actually more electronegative than lithium, so it goes like that. Carbon, not really much of a dipole arrow, it's very weak. And then we have a strong dipole arrow for HF. And so this one is not acidic at all. This would actually act as a hydride, something we'll kind of touch, well, we won't really touch much on that. But you can see it can't release an H plus. If this were to break into anything, it would break up into H minus and Li plus, right? Where an acid is H plus. So they are indeed different things. In the center here, we have a very weak dipole. And so in general, this is not acidic. Which is good because most of biological things are made out of CH bonds. So if these bonds were breaking and reforming all the time, that would spell big trouble for us. And then this bond here is acidic because we have this polarized bond. We have a partial positive hydrogen. And so you can think about partial positive, that's much closer to being actually positive and releasing an H plus. So when we take a look at the periodic table, when we go from left to right, we increase the electronegativity, right? And so we make the bond more polar. And so we get a stronger acid, right? And what we're talking about here are binary acids. So it's an H plus one other element. So if we think about the periodic table, here we've got nitrogen, oxygen, fluorine, and then under them we've got phosphorus, sulfur, and then chlorine. And so if you think about these forms, right, we'd have NH3, nitrogen is going to want to form 3 bonds, H2O, hydrogen or oxygen is going to want to form 2, and then HF, the halogens are going to want to form 1. This guy, ammonia, is actually a weak base. Water is neutral. And then HF, hydrofluoric acid, is actually a weak acid. So we can see when we go from left to right and increase the electronegativity, we make this bond more polar. Thus, we make it easier to release this H+. And same thing in this kind of next row, pH3, H2S, and then HCl. This is actually a weak base. H2S is a weak acid. And then HCl is a strong acid. Right. So again, when we go from left to right, we see an increase in acid strength due to this difference in electronegativity. And again, it's all about making this H, whatever it's bonded to, bond weaker. Then we can ask ourselves, what about when we go down the periodic table? Does this hold true? And so when you go down the periodic table, so electronegativity decreases as we go down. So you may predict that acidity decreases. Right, you go down, you get less electronegativity, less electronegative, so the difference in electronegativity decreases, so you become less acidic. But unfortunately, this is actually wrong. And we'll take a look at why. So for example, in this above, we have H2O, right? And below oxygen, we have H2S, right? Water is neutral, while H2S is a weak acid. So you see when we went down the periodic table, we actually got more acidic. Then we have HF over here, which is a weak acid. And then right below it is chlorine. So HCl, this is a strong acid. So based on the evidence, when we go down the periodic table, we actually get more and more acidic. And so the reasoning for this is that bond strength isn't just determined by polarity. There are other factors that control this bond strength. And so another thing that controls this bond strength is the relative size or polarizability of the atoms. And so when things are of similar size, their bond is stronger. And when they're of dissimilar size, then their bond gets weaker. This is known as HSAB, hard soft acid base theory. The acid and the base in this case is actually not referring to the H+. It's actually a little bit more complicated than that. We're just going to take it very simple. So if we think about H, it's relatively about this size, and then we think about fluorine, they're relatively the same size. And so this bond right here is overall strong or relatively strong. Whereas when we go down the periodic table, the elements get bigger and bigger and bigger. Obviously, hydrogen's not going to change its size, but if we think about something like HI, iodine is much bigger than fluorine. And so we have a size mismatch, and that causes this bond to be weaker. Right. So when we have this size mismatch, overall, we get a weaker bond. It actually does get more complicated than this. It also has to do with the stability of the conjugate base and entropic effects. It gets more complicated pretty quickly. But basically what we want to know from this summary here, so binary acids summary, And that's basically when we go towards the bottom right, we get a stronger and stronger base, or stronger and stronger acid, my bad. So nitrogen, oxygen, fluorine, here's our periodic table, phosphorus, sulfur, chlorine, then selenium and bromine. When we go from left to right, we get a stronger acid. And then when we go from top to bottom, we get an even stronger acid. Let's picture this. And the cause of this effect is when we're going from left to right, we're making a more polar bond. And then when we go down the periodic table, we have the size mismatch along with some other factors. But it's all, again, about making that bond weaker and weaker. And the weaker your bond, the stronger your acid.